Okay, good morning. So today it's a great pleasure to have Professor Subir Das from JNCSR Bangalore to speak on part of the program. He's an expert in critical phenomena, and he will be talking about various aspects of dynamics during phase transitions. Thank you.
Okay, let me start by thanking the organizers for the kind invitation. And the crowd, as I said already, 50% are from JNC. And anyway, let me start. This has, the reason behind the thin crowd is related to the major part of the program is, main part is over or something like that. In any case, so I'll talk about essentially diversity in dynamics of phase transitions, and emphasis will be on structure dynamics connection in various kind of phase transitions. And whenever we talk about phase transition, quite naturally, the concept of universality comes in. So it will be quite natural to give a general overview of what we mean by universality. And this universality I will discuss in the context of static critical phenomena, dynamic critical phenomena, as well as kinetics of phase transition. And then I will present results from nucleation and growth in vapor liquid and vapor solid phase transitions. In the abstract, I mentioned about presenting results from two different kind of models. One is, say, Lennard-Jones model, and another one is our good old Ising model. But I realized that I won't be able to cover the second one in this talk, so I will primarily confine to the Lennard-Jones model, and in that context, I will present results from vapor liquid and vapor solid phase transitions, and certainly I will end with the customary conclusion. So let me start by giving a general introduction about phase transition and critical phenomena. This is the very popular phase diagram in pressure temperature plane. Various different phases are marked. They're separated from each other by various continuous or broken lines. And along these coexistence curves, two different phases can coexist with each other being in equilibrium. And this vapor-liquid coexistence curve terminates at a certain point, referred to as the critical point. And if we look at this particular part of the coexistence curve in temperature versus density plane, the coexistence curve looks like this. And this is my low-density vapor branch, and this is my high-density liquid branch. And at very high temperature, we have a situation like this. You have supercritical gas phase, and when you quench such a system by lowering the temperature inside this coexistence curve, you see two different phases. At the top, you have the vapor phase, and at the bottom, you have liquid phase, and they coexist with each other, being separated from each other by this interface. And close to the critical point, you have this huge density fluctuation. And critical phenomena is about this density or the order parameter fluctuation. And in the case of perfectly symmetric phase diagram like this, so by the way, vapor liquid phase diagram is never so symmetric, but this has been drawn for the sake of convenience. I mean to say that the symmetry is in the sense that drawing by hand an asymmetric curve is little difficult. So whenever you have such symmetric situation, your order parameter can be appropriately defined as rho minus rho c. Here, this is the critical density, this is the critical temperature. And more generally, in an asymmetric situation, you can define your order parameter as the difference between densities in the liquid and vapor phases. And then people would like to understand the structure of fluctuation in the vicinity of the critical point. So if your phi of r is the space-dependent fluctuation, then the structure can be obtained by the calculation of this correlation function. And typically, the correlation function has this sort of functional form. I call it Ornstein-Zernike-Fisher form. I mean, more popularly, this is known as the Ornstein-Zernike form. Now, this power law exponent P contains the exponent eta, which is the Fisher exponent. So when you combine this thing, it's quite natural. I mean, I prefer to call it Ornstein-Zernike-Fisher form. And here, this xi is the correlation length. So that gives you information on the correlated distance in the system, which is a central quantity, and it diverges at the critical point as a function of the deviation of temperature from the critical value with some exponent nu. Okay? So this epsilon is essentially a reduced temperature, essentially the deviation of temperature from the critical point. Okay. Yeah, it goes away. Okay, in the previous slide, I already defined a couple of critical exponents. One is this eta, okay, part of the power law exponent P in the correlation function, and nu related to the divergence of the correlation length. And here, in addition to the divergence of the correlation length, there are several other quantities which show analogous power law singularities. That is the order parameter that vanishes at the critical point when you move from the lower side with some exponent beta. The susceptibility diverges with some exponent gamma. Specific heat diverges weakly with some exponent alpha, so on and so forth. And interesting fact about critical point phenomena is that all these exponents are not independent of each other. They are connected to each other via certain scaling laws. I just noted down few of them. And all these scaling laws can be obtained from the famous simple scaling hypothesis of Benjamin Widom. That is, a dimensionless quantity will be invariant and others will change according to their dimensions, and near the critical point, the correlation length is the only characteristic length scale. And other important and more beautiful fact about critical phenomena is the presence of universality. So what I mean by that, the values of the exponents are quite universal. They of course depend upon space dimensionality, order parameter symmetry, and range of interaction, but do not depend on the material and type of transition. By material and type of transition, I do mean that, so critical phenomena is essentially about second order phase transition. So I'm not talking about first order or second order in the type of transition sense. I'm talking about it can be a transition from para to ferromagnetic phase, it can be vapor-liquid transition, it can be liquid-liquid transition, it can be phase separation in a binary mixture, okay, so on and so forth. So irrespective of all those transitions, if the space dimensionality, order parameter dimensionality, by order parameter symmetry, I mean the number of components in the order parameter. And for example, if you are talking about an uniaxial ferromagnet, then Ising model describes the scenario quite well, and you have a scalar order parameter, or in vector sense you have order parameter component 1, and if you are interested in the study of a planar ferromagnet, for that you need another component that is referred to as the XY model, and in the more general situation you need Heisenberg model. So that is very much isotropic. The atomic magnets can align in any direction in countable space, and there you have order parameter symmetry equal to 3. So these are called ON symmetric model. N is the number of components in your order parameter. So irrespective of all those types of transition, if your system dimension is same, order parameter symmetry remains same, and range of interaction remains same. By range of interaction, I mean to say, so it is basically demarcated by if the interaction strength decreases faster than 1 over r to the power d, one calls it short range interaction. Of course, there is some another additive term sigma, which is roughly equal to 2, but let's forget about it in this context. So if it is faster than this, then we call it short range interaction, and there the universality is described nicely by the Ising universality class. So if all these factors remain same, okay, for example, in d equal to 3, if you have a scalar order parameter and short range interaction, irrespective of whatever type of transition you have and whatever material you have, doesn't matter. So the values of the exponents will be given by these numbers. Okay, so there are a couple of other things, delta, eta is usually very small in d equal to 3. And there is another universality class, that is the classical universality class or the mean field universality class, where your interaction decay is slower than this, then you have such and such numbers.
But you don't really want like Coulomb interaction, that's a different story.
Well, that actually belongs to the Ising universality class. That is because you have screening in the system and effectively you have short range interactions. So,
no, but if you have true Coulomb, you cannot do this, right?
True Coulomb, I mean, if it doesn't belong to this, you expect this to belong to the long range universality class.
Okay.
Well, mean field, in a sense, it contains the long range interaction. So if you go to the solution, the way it is done, so you have a central spin that interacts in a mean way with the rest of the system. So that essentially brings in a long range interaction to the system. Okay, but that is a matter of debate. Now, about the Coulomb system, so there, Fisher spent about 10 years. So it's related to electrolyte system. If you have overall electroneutrality in the system.
Yeah. Is fine. All I was saying is that it doesn't matter.
Okay. And this universality I tried to depict by these couple of pictures that which are taken from the book by Eugene Stanley. So here you have vapor liquid transition exhibited by various different types of materials, and for each of them certainly the critical temperature and critical density are different. Now if you scale the temperature and density axis by the corresponding critical values, you can superimpose all the curves on top of each other. That says that the such kind of universality does exist. And this is, and the corresponding value is essentially close to 0.325. And this is the depiction for antiferromagnetic transition. Here I have plotted phi cube versus epsilon, and you can see that nicely data are consistent with the linear behavior that confirms that beta equal to 0.325 or 1/3. Yeah. And you can do similar exercise related to other exponents, but I'm not going to spend time on that. So critical phenomena, as I said, correlation length is the central quantity, and it diverges at the critical point. And we also know that a system tries to relax itself. If you slightly perturb, it tries to relax itself over the characteristic length scale. When that correlation length diverges, which is the characteristic length scale at the critical point or in the close neighborhood of the critical point, then it is expected that close to the criticality there will be a slowing down of fluctuations. Okay? And that slowing down of fluctuation can be captured by this dynamic structure factor. Okay? So through this exponential decay, and argument of which contains the thermal diffusivity in the vapor-liquid transition context. And previously people thought this dynamic critical phenomena that is expected to capture the critical slowing down should be dictated entirely by the static criticality. Okay, what do I mean by static criticality? So these are all thermodynamic quantities, okay, and the phenomena exhibited by the thermodynamic quantities are referred to as the static critical phenomena, and then the corresponding dynamic part is referred to as the dynamic critical phenomena that captures the critical slowing down of fluctuations. So as I mentioned, till mid-60s, people thought that the dynamic part will be completely dominated by the static critical phenomena or static singularities. Now, this diffusivity, the thermal diffusivity, which is the relevant quantity in the context of dynamics, vapor-liquid transition, that is the ratio of a pure dynamic quantity and a thermodynamic quantity. Okay? So this lambda is the thermal conductivity and kT is the compressibility. So it's actually lambda over Cp. Cp has in the vapor liquid context similar divergence as the compressibility, okay, unlike the Cv which has alpha singularity. Okay. Now Kt diverges at critical point, the static quantity. People thought that the lambda will remain finite, but experiments of Ian Sengers actually showed that lambda has its own critical existence, which is a pure dynamic quantity. So these are experimental results close to the critical point. As a function of density, these things are plotted. As you can see, as you approach closer and closer to the critical point, the peak gets sharper and sharper. I think these are neutron scattering experiments. So this is the thermal conductivity, but I don't know how exactly they have measured it. And in the dynamic context also, there exists the scaling relations of this type, okay? And I will just give one example. So this is my thermal diffusivity, and all of you are aware of Stokes-Einstein relation. Here I write Stokes-Einstein-Sutherland relation, okay? Are you aware of the history? But you are familiar with this kind of relation, Stokes-Einstein relation. Typically, you study in the context of self-diffusion constant, that is the single particle diffusivity, that is often denoted by ds or simply d. So there, the right-hand side is kBt divided by 6 pi eta times A. A is the hydrodynamic diameter of the particles, okay? And that is related to single particle diffusivity, eta is the shear viscosity, etc. And this, this is a more generalized expression in the context of collective diffusivity. By collective diffusivity, I mean that involves, so this is different from self-diffusion, okay? And if it is collective, and we are talking about critical phenomena where we have divergence of the characteristic length scale, so we have to replace the single particle hydrodynamic diameter by the corresponding correlation length, which is diverging. And the Stokes-Einstein-Sutherland, why I call Sutherland, Einstein's paper on this fluctuation dissipation was published in 1905. That was one of his 3 famous papers of 1905. And in 1904, William Sutherland is an Australian physicist. That time he was more, better known than Einstein. And in 1904, similar result he published in a Royal Society journal, but later people did forget about Sutherland. Naturally, Einstein became more popular. Anyway, so since early 2000, 2005 or 6, people started calling it Stokes-Einstein-Sutherland relation. And now if you start with this thing, then you invoke the critical divergence of xi, then there will be critical slowing down, and that's what I am talking about. So the shear viscosity or viscosity of any type, shear or bulk viscosity, that should diverge also at the critical point, because the dynamics is becoming slow. Okay? Dynamics becoming slow, that means your diffusivity will tend to vanish and the viscosity will tend to diverge. Okay? So, so that one is not self-contradictory with the other. And if you invoke the divergences of eta and xi, then actually you end up with such kind of scaling relation like the static ones. And analogous relations exist with respect to the slowest relaxation time in the system. So that is the relaxation time tau should diverge at the criticality with some exponent z. Okay? And this z has actually different values for different types of transitions. For example, for para to ferromagnetic transition, the value of the dynamic exponent z is 2. For fluid-fluid transition, value of z is 3. For phase separation in solid binary mixture, the value of z is 4. Now recall that for all these different types of transitions, the static critical exponents are all same. Okay? What I want to conclude or emphasize here, that unlike the static critical phenomena, the dynamic part is with respect to universality is much weaker. Okay? Despite the fact that in all these transitions will give rise to same, if your system dimensionality, order parameters, symmetry, and all those parameters I have mentioned in the second slide. Yeah. These are 3D things.
Because in 2D you have an exact mapping between the model and the EPS.
No, the dynamics. Dynamics. So, are you going to talk about the dynamics?
Yes, yes.
Non-conserved, conserved, etc.
Yes, this is the non-conserved thing. This is the conserved thing.
Static universality class. But magnetization might be conserved or not conserved, but the fluid, the density is conserved. The dynamic exponent depends on whether your slow variable is conserved or not.
Okay. So in both these examples, fluid-fluid transition and phase separation in solid binary mixture, the order parameter is conserved, but the dynamic exponents are different.
But there is an understanding, right?
Yes. I'm not saying it's without any reason. There exist reasons. But the beauty of static part is that despite all these differences in the dynamics, you get similar or exactly same critical static critical exponents. Okay. So that was about equilibrium dynamics, where you can apply. So when you talk about equilibrium dynamics, there exists some sort of non-equilibriumness in local sense. Okay. Or in other words, you can say if you slightly perturb the system, okay, then your interest is to see how the system relaxes back to the equilibrium. Okay. If there is no local non-equilibriumness in the system, everything will be perfectly static in its own place. There will be no transport in the system. So when we talk about equilibrium dynamics, there also exists certain non-equilibrium feature. So in that, and there basically you can apply linear response theory, so on and so forth. Okay. So in any case, we are calling it equilibrium dynamics. Now I move to a situation where you are far, far away from equilibrium. Okay. So once again, I show this coexistence curve, and far, far equilibrium, I want to mean the kinetics of phase transition when, say, you prepare your system at a very high temperature and quench, make a deep quench inside the coexistence curve, system falls unstable to fluctuation, and it tries to evolve to a final equilibrium. If your system is finite, if it is infinite, the evolution continues forever. Okay. Now, before getting into the details of the kinetics, let me briefly state a few things in the free energy context. So we know that free energy minima or minimum occurs at equilibrium values of the order parameter psi. So here there is a symbol mismatch, so read it as phi. Okay. So when you are at a very high temperature, you know that your system is homogeneous, and the way you have defined your order parameter that has value 0, so your free energy curve will have this kind of shape. On the other hand, when you have quenched the system inside the coexistence curve, then say in the non-conserved sense, if you are interested in the ordering of a ferromagnet, okay, then and you are starting by Ising model, all your spins will be either up or down, okay, and then both of them are equally symmetric with respect to each other. That way, basically, you expect two minima symmetrically located around the value 0, and you get this kind of shape. And what was the minimum at high temperature, after the quench that has become a maximum. So that says that the system has fallen out of unstable to fluctuation, and then it tries to reach any one of these minima. And how the system evolves from this unstable situation to those one of these locations, that is the subject of kinetics of phase transition. Okay, and once you quench, this kinetics proceeds by the formation of particle rich and particle poor domains, and those domains grow with time. And this growth is a self-similar phenomena in the sense that in a statistical sense, so that if you pick up a pattern at a later time and scale the size by some appropriate number, if you pick up these and multiply it by a number smaller than 1, then in a statistical sense you can superimpose this one on top of this. And this structure can be understood by the calculation of this 2-point equal time correlation function. Recall, it is the same as this correlation function that I have defined here, but here there was no time involved. And since we are talking about highly non-equilibrium situation, we have invoked the time. And then this self-similarity fact is reflected in the scaling behavior of the correlation function in such a way that if you, so this is my correlation function and this is my distance axis. I have presented data from few different times, and for each of the time, if you pick up the correct value of the average domain size and scale the distance axis by those respective lengths, then data from different system size times will overlap on top of each other. So that means there is a scaling of this type in the system. Okay, and such multiplicative self-similarity already says that the growth will occur in a parallel fashion with time with some exponent alpha. And recall that in the equilibrium dynamics context, we wrote down such a relation for the relaxation of the system. And this looks very similar to this. And in a sense, even though we are talking about these quenching experiments are essentially first order phase transition experiments, even though the order of transition differs, there exists certain similarity. So in a sense, like this is also a critical phenomena. Okay? And if so, it makes sense to search for universality. Yeah. Estimate of time scale, basically, if you have a finite system, so as I said,
it never pays up.
yeah, so that's what I mentioned.
Yeah, but it also depends on the distance. As you go lower in temperature, these characteristics become.
Well, yes. As you go lower and lower in temperature, the kinetics will slow down because your diffusion constant will get lower and lower, so on and so forth. And in the conserved dynamics context, so the system will get stuck in metastable states. And it may so happen that the system never reaches the ground state.
But it will never reach ground state.
Yeah, if it is thermodynamically large, I already mentioned that is the case. The growth will continue forever, whatever temperature you are at. Okay?
So for a finite system, you actually will interrupt the scaling law at some time.
Right, right. This exponent z is not, it's the exponent related to the relaxation, how the system, so system will relax, try to equilibrate itself over the characteristic length scale. Okay. So as the characteristic length scale increases, that means you go closer and closer to the critical point, the relaxation time should grow more and more because the correlation length itself, the characteristic length scale itself is growing bigger and bigger. Okay, so your equilibration will take longer and longer. Okay. Okay. Now, yeah, I state again, so your characteristic length scale in the far from equilibrium situation is expected to grow in parallel fashion with time t in this fashion. And in that context, I mentioned it is like critical phenomena. So if you make a substitution or mapping from time to 1 over epsilon, see, epsilon is the quantity with respect to which the static correlation length diverges. Okay? And time is the thing with which the non-equilibrium domain size diverges. Okay? So that way, basically, if you make this one-to-one mapping from T to 1 over E, so it essentially looks like the critical phenomena picture. Okay? Now, we ask the question, is their universality. And in the equilibrium dynamics context, I mentioned that universality is far weaker compared to the static phenomena. And here I am going to say that in the non-equilibrium dynamics, the situation is even worse. The universality is very, very weak. Okay? For example, if you consider ordering in ferromagnets, you have prepared your system at very high temperature in a paramagnetic phase, then you make a sudden quench. Below the Curie temperature, you are in the paramagnetic phase. Then how the ordering occurs in the system, there the value of alpha is 1/2. Now, when you have phase separation in solid mixtures, okay, say you have two components A and B, you prepare the system at very high temperature where A and B particles are perfectly mixed with each other, then quench inside the coexistence curve, you have alpha equal to 1/3. Okay? Now, so these two are different depending on, so in this case there is conservation, there is no conservation of the order parameter, and in this case there is conservation of order parameter. So this conservation of order parameter brings in certain difference. But it is not, the exponent value is not same always even if the order parameter is conserved. For example, if you move from solid to liquid, the situation is where not only the exponent is different, a single exponent doesn't describe the full growth. Okay? So initially you have an exponent 1/3, then that crosses over to value 1, then there is a further crossover to value 2/3. Okay? And this is the situation when you have quenched along this particular line so that you have a percolating morphology like this. So this is what I call interconnected or percolating morphology. But if you quench along a different line, say in a vapor liquid transition, your overall density is close to the vapor branch of the coexistence curve so that you have a disconnected morphology like this. This is the nucleation and growth regime. Here, nucleation of liquid droplets occur and they grow with time by a different kind of mechanism. So that's what I call disconnected droplet morphology, and this is percolating morphology. This is in 3D. The corresponding picture in 2D looks somewhat similar to this. Yeah. In very high density, you have bubbles, disconnected bubbles. Okay? Okay. So in the disconnected case, you expect alpha equal to 1/3 all through, but for a different, the mechanisms are different in the two cases. Okay? Now, if we go to vapor liquid, so this was for the liquid phase separation. If we go to vapor liquid phase separation, there also there will be some such kind of morphology dependence. We expect the same picture for the percolating case, and in the disconnected case, alpha may be 1/3. I will describe all these things in more detail. Disconnected means you have morphology like this. If you have very low supersaturation in the system, okay, then the structure cannot percolate. Okay, you will have formation of small droplets of liquid, okay, and then the growth can occur due to various different types of mechanisms. I will describe those things. On the other hand, if you have very high supersaturation so that you are in the critical density region, then you will have such kind of interconnected morphology. Okay. Okay. So, and if we go to vapor solid phase separation, there also things should depend upon morphology, but the situation can become even more complex, and liquid solid phase separation is even more tough. Okay? I will just touch upon all these things as I move along. So what I mean to say that is a whole zoo of things. We started with very universal static critical phenomena, then moved to equilibrium dynamic critical phenomena. Already the universality was weaker, and then if we move to kinetics of phase separation, that means far from equilibrium dynamics, then you see all sorts of, I just noted down a few of them. Okay. Essentially, these are all related to first order transitions. All of these do not have even a second order endpoint, like the vapor solid transition or liquid solid transition. They do not end at a second order transition. Okay. Anyway, the focus of this talk will be in the disconnected case. So as you and others asked the question, so it is important to understand what I mean by disconnected and connected morphology. So I'll come to that point again. So I'll focus on disconnected morphology in the context of both vapor liquid and vapor solid transition, and all these things will happen in the nucleation and growth regime. So when I want to talk about nucleation and growth in the nucleation and growth regime, it's good to recap our ideas of what we mean by nucleation and growth. Let me start with this coexistence curve again. So typically people draw another boundary, a dashed line like this. That's what is referred to as the spinodal line. I do not believe in the existence of spinodal line, okay? But for kinetic purpose, it is often useful to draw such a line. So what I mean to say, if you are inside that spinodal line, the phase separation starts spontaneously, and typically during the growth process, the structure is bicontinuous or interconnected or percolating like this. And when you are in this region or in this region, if you are here in a vapor liquid context, you will have disconnected liquid droplets, and if you are here, you will have disconnected bubbles or disconnected vapor droplets. Okay? The question is, how do they grow? Before that, let me describe the equilibrium picture in a little bit more detail. Anyway, so these are just few examples of nucleation. Okay? It is very abundant everywhere. Crystallization in liquid, formation of cloud droplets around cloud condensation nuclei. In biology, you have one of the most difficult questions to answer is the nucleation related to how life forms. Then formation of bubbles in a Coca-Cola bottle, or for that matter, any other cold drink bottle, okay? Nucleation of quark gluon plasma, or formation of hadronic composite. This is related to particle physics. Accumulation of cosmic dust to form planetlets. These are all related to nucleation. So it's a rather diverse topic. And the primary work that I'm going to discuss today, that has relation with this astrophysical example to a good extent. Now this nucleation is essentially the formation of embryo or nucleus with the introduction of boundary between two phases. Whenever nucleation occurs, for example, in a vapor liquid transition, if a liquid droplet forms, that forms at the background of a vapor phase, that means a boundary separates the liquid droplet from the vapor phase. So all nucleation occurs at the cost of formation of an interface. That is the boundary I am talking about. And then there are different varieties of nucleation. One is called homogeneous nucleation, that occurs in absence of any impurity. And in reality, there exists impurity always. For example, if you talk about formation of liquid droplets in upper atmosphere, in cloud, and so on, often it happens in presence of impurity. Basically, these are all surface-induced heterogeneous nucleation. Okay, so heterogeneous nucleation means nucleation in presence of impurity. Okay, and then what are the different type of questions people do ask in the equilibrium context, and for that matter in non-equilibrium context also. So before getting into the non-equilibrium context, let me start by writing down the free energy for the formation of a nucleus. So there is a volume contribution. This is the volume part of the droplet, and there is an interfacial part. Okay, and volume part should be proportional to r cube, and the interfacial, this is the free energy density per unit volume, and this is for the interfacial part, this is my interfacial tension, and it should be multiplied by r square because I'm talking about the surface, okay? And there are differences, there is difference in sign for the volume part and the surface part. This is because in the volume part, particles like each other. On the other hand, across the interface, if you take the example of Ising model, for example, in the Ising model context, such a nucleation nucleus will form either with all spins up or all spins down, okay? And if you recall the ferromagnetic Ising model Hamiltonian, so you have J, Si, Sj with the negative sign, J is positive in the case of ferromagnetic transition. Sorry. There, when all spins are aligned in the same direction within this nucleus, you can imagine that the energy will be negative. If you are in the ground state, I'm not bringing in entropy and all those things into the picture. On the other hand, across the interface, on one side you have up, another side you have down. You have positive contribution to the Hamiltonian, to the energy, okay? But I can describe it more clearly with respect to chemical potential, but I'm not getting into the details. So there is a volume contribution, there is an interfacial contribution, sign difference, competition.
Sorry, Subir. What you talked about is the surface tension. The fact that you're breaking bonds. That's only the surface tension.
Yeah.
The only way you'll get a delta F nu is if I have a field in the Ising model. In the model at zero field, there's no difference.
Yeah.
So that's going away, right?
Yeah.
So that's the
Right. So there is a competition. That way, basically, the free energy curve will look like this, and there will be a maximum. And this maximum is basically the free energy barrier that one needs to overcome for the formation of a stable nucleus. And the corresponding radius is the critical radius. Okay? If by chance, because of some small length scale fluctuation, some droplets form with size of the radius smaller than the critical value, they will disintegrate. Okay? And by chance, if there is a large wavelength fluctuation, okay, and because of such large wavelength fluctuation, a big droplet forms with size larger than this critical value, they will be stable and they will grow with time. Okay? And this growth is the topic of discussion. But before getting into that, let me just briefly summarize what all different types of interest do exist among people. So people are interested in finding out the critical radius, the barrier, the interfacial tension, and rate of nucleation, which is essentially Arrhenius like this. And another aspect, so the classical nucleation theory, so what I wrote here, the surface term, 4 pi r square times gamma, this is the traditional classical nucleation theory picture. Gamma is the interfacial tension where people do take gamma as the value for flat interface. Okay? Now, since we are talking about quenching along a line close to the coexistence curve where you do not expect really a flat interface, you have droplet structure, so there is certain radius of curvature, people are interested in the curvature dependence of interfacial tension. How the, sorry? It's not a, so delta F is, yeah, so that will take care of it. Okay, and so Richard Tolman, long time back, these are kind of heroes, uncelebrated heroes. By the way, Richard Feynman was a Tolman professor, okay? Anyway, so he wrote down such an expression. So this is nothing but expanding the downstairs in 1 over r. Taylor expansion and truncating after the first order correction, okay? But this way of writing, there was no physical justification at that point, and this delta is referred to as the Tolman length. So this is the kind of correction, leading order correction people did expect up to, say, 1980s or so. Then Matthew Fisher and Mike Vortis showed that for symmetric models, basically this Tolman length will be absent. I can give you the reasoning for that, but I think I'm moving rather slow. Okay. So the leading order correction for symmetric model, it will be like this. Then people also got interested in the critical behavior of this curvature dependent interfacial tension, and recently we wrote down a rather general universal expression for the critical behavior of this surface tension. So again, this says that the whatever transition you consider and wherever in the phase diagram you are, if you are talking about static critical phenomena, you can obtain such kind of universal relation, which is not true for dynamics. What I am going to say and already mentioned briefly, number one, even for a particular, for quenches and along a particular line, dynamics is different, dynamical exponents are different. On top of that, if you move your quenching point along this line, there can be vast diversity. Okay? Unlike such kind of things in the static context. Okay. Now I come to the growth part in the disconnected morphology. Is it clear to you that if you quench along different lines, like if you quench along this line, if you quench along this line, you will get different morphologies. Okay? So this is the disconnected morphology, this is the connected morphology. When you have high overall density, the liquid domains are connected. It percolates through the whole system. When you have very low overall density, then the liquid droplets, they cannot, they form such kind of disconnected morphology. So I gave a brief introduction to nucleation in the static context. Now I am going to talk about the dynamics when you quench along a line where your end point is close to the vapor branch of the coexistence line. Okay? It can be vapor solid transition, it can be vapor liquid transition. Okay? Both the transitions I will discuss about. By the way, I started probably at about, no, 11:30 I guess. Okay, so this is an example of growth of ice clusters, and this is certainly related to vapor solid transition, and this is an example related to growth of liquid droplets, okay, water droplets for example, so certainly related to, in the vapor background, related to vapor liquid transition. Now you can see structural difference, even though in both the cases the clusters and droplets are disconnected, the pattern is disconnected. Okay? Here, one cluster is separated from the other.
What's growing? This is ice growing in liquid? So
this is vapor.
Vapor. So this is solid vapor?
This is vapor solid, this is vapor liquid. Okay? In the vapor liquid case, the liquid droplets have spherical symmetry. Okay? On the other hand, the structures are fractal in the vapor solid case. Okay? I'll come into the reasoning behind this, but before that, I ask the question, what can be the different ways of growth for disconnected morphology? Okay? Now, in both the cases, these droplets or clusters do consist of many small particles. And a very simple scenario which is true for say growth in solid binary mixture, particles from smaller droplets or clusters get detached to be deposited on a bigger droplet. Okay? This is basically Oswald ripening, rich eating up the poor. Okay? So you can imagine particles getting detached from a small cluster, and due to a concentration gradient, they're diffusively moving and getting deposited on a bigger cluster. That way, basically, a smaller droplet or cluster will vanish over a period of time. That way, the number of droplets in the system will decrease, so the average size will increase because there is mass conservation. And another picture can be these clusters or droplets, they themselves can move. And this is highly possible when the background phase is a fluid phase, either a liquid or a vapor phase, which is not possible when you have solid binary mixtures. Essentially, droplets themselves are kind of static in their location. Only individual particles will get detached from those clusters, and they will diffusively move towards a bigger cluster, okay, to make big even bigger and small even smaller. Now, in the fluid where the clusters themselves can move, the picture will be different. And these moving clusters, they will undergo once in a while some sort of sticky collisions. They'll collide with each other and stick to each other. That way, all of a sudden, a bigger droplet will form. A bigger droplet will form, and naturally, yes. This is a sort of collective diffusion, okay. This is a collective diffusion. I will not identify it with this collective thermal diffusivity or concentration diffusivity. There exists certain difference, but this is also a collective diffusion, okay. And so the growth can occur by a different mechanism. Now the question is, when you have a fluid background, the question is, this motion of the droplets, this collective motion of the droplets can happen by various different mechanisms. One can be diffusive, it can be ballistic, it can be subdiffusive, super diffusive with different exponents for the mean square displacement. It can be super ballistic also. For example, if you have certain external field in the system, in case of active matter system, people can collectively enhance their velocity because of certain reason, okay. So it's a whole zoo of a thing. So again I come back, briefly describe all the pictures. So one is the Oswald ripening picture, where you have a solid binary mixture, for example. Their particles will get detached from a smaller droplet to be deposited on a bigger droplet. That way, you can write down the interface velocity, okay, which is the rate of growth of the average domain size, okay, to be proportional to the gradient in the chemical potential. So because that's what is driving the motion of driving the transport in the system. And via some dimensional argument, you can write the whole thing as this. One L downstairs come because of this gradient, and another L comes dimensionally because chemical potential is interfacial tension over L. And when you solve this equation, you get alpha equal to 1/3. This is the Lipschitz-Liouville picture. And when you have liquid-liquid transition, okay, as opposed to solid-solid case, I mentioned that the droplets themselves can move, and once in a while they will collide. And this collision rate is typically proportional to n square, where n is the density of droplets, not the density of particles, the density of droplets. And because of these sticky collisions, there will be a change in the droplet density. That's why this dn dt term. And the negative sign is because of the fact that due to collision, the droplet density decreases, okay. And the time scale can be further modified by bringing in a couple of other things. One is, so I'm talking about actually droplet diffusion mechanisms. The transport here is diffusive. The droplets are moving diffusively, okay. So one time scale will come from the mobility of the droplets, how fast they are diffusing, and another one will come from how large these droplets are, okay. So, and this dl by the Stokes-Einstein-Sutherland relation is a constant. So you end up getting a simple differential equation, dn dt is proportional to n square. And because of the conservation of mass, this droplet density is proportional to the average volume of the clusters or droplets. So if you...
just to make sure, the connection to the Sutherland is L is your correlation.
Yes, yes. Yeah, or in the single particle situation, L is your single particle hydrodynamic diameter, okay? Okay, so if you replace this expression for n into this equation, you get a differential equation in terms of the characteristic length scale. You solve this, you get this growth exponent 1 over d. So it's the dimension dependent growth exponent. So you can see, so when I mentioned about all these exponents here, these are related to 3 dimensions only. And there I mentioned that in the disconnected case, in liquid mixture, alpha is 1/3 because of this droplet diffusion and coalescence mechanism, and that has the value 1/3 only in d equal to 3, and in d equal to 2, it has a different value. So things are getting even more complex. Now, what will be the picture in vapor liquid case? Vapor phase is of very low density, okay? So there one can imagine that the liquid droplet can move kind of freely. That may give rise to some sort of ballistic aggregation picture. But if your quench temperature is not low enough, reasonably close to the critical temperature, the background vapor density won't be that low. There will be some degree of resistance, viscosity offered by the background density. On top of that, there will be some fluctuations in the density if you are close enough to the critical point. That way, basically, these liquid droplets will experience kicks from here and there, making the motion of the droplets kind of random walk type, so that this diffusive coalescence mechanism may still be valid. Okay? So this is the picture for vapor liquid for high vapor density. Okay? This Binder and Stauffer picture may still be valid. Now, what about vapor solid transition? This is my triple point line. Vapor solid transition will be at a very, very low temperature, where if you look at this coexistence curve, you can imagine that the background density will be very, very low. The droplets or clusters will kind of move in a force-free, in a resistance-free situation for a long, long time. Okay? So there you can capture a situation which is analogous to ballistic aggregation that people talk about in astrophysical context. Growth in cosmic dust, so on and so forth. There, of course, gravity is important, but if you talk about formation of small, small planetlets, unless those objects are not very close to each other, the gravity can be neglected. That way, basically, this thing has similarity with such kind of situation. Okay? Okay. Now, to study both of these vapor liquid and vapor solid transition, in the phase transition, we consider a Lennard-Jones simple single component Lennard-Jones model. And first thing is to look at the phase behavior. These phase diagrams are obtained from very sophisticated Monte Carlo techniques, both in 2 and 3D. You can see that the critical numbers are different and the shape of the curves are different because this is 2 dimension, this is 3 dimension. Okay? Different critical temperatures. That's because of the missing, in the case of 2D, the critical temperature is less than 3D. That you can imagine is because of the less number of nearest neighbors in the 2-dimensional case. Okay? I'm not getting into the details about that. So we'll perform, to study the kinetics with this model, we'll perform molecular dynamics simulation. First thing I will briefly mention about the vapor-liquid transition in the disconnected situation. Nucleation is occurring and the stable nuclei are forming via the...
You're not going to tell them what model H is?
Okay. Okay. Model H is a... So for that I need to define first Cahn-Hilliard equation.
What's conserved and what's not?
So model H is a conserved dynamical model, and it is according to the nomenclature of Hohenberg and Halperin. I spoke about phase separation in solid binary mixture, and that one way of studying that is via the Monte Carlo simulation of Ising model. On the other hand, you can actually, so there the order parameter is conserved your density field is conserved. And you can study that thing via the Monte Carlo simulation of Ising model, for example. On the other hand, there have been a community who prefer to, I also study in both the ways, basically Monte Carlo and by writing down various different continuum dynamical equations. So there you introduce Ginzburg-Landau free energy functional, okay, and put that free energy functional in an equation of continuity, okay. That way you get the order parameter there is a continuous variable, and that describes your phase separation in solid binary mixture. Now, when you are interested in fluid, okay, and in fluid hydrodynamics is important, velocity field plays important role. So you combine, so this Ginzburg-Landau picture, putting it into the continuity, equation of continuity, the resultant equation that you get, that is called the Cahn-Hilliard equation, okay. And you combine the Cahn-Hilliard equation or couple the Cahn-Hilliard equation with the Navier-Stokes equation that takes care of your velocity field, okay. And in the Navier-Stokes equation, so the question is, how do you couple the two equations? In the Navier-Stokes equation, you have current due to velocity, and an additional current you bring in due to the chemical potential difference in the order parameter field, and then you bring another similar thing in the Cahn-Hilliard equation, a current from the velocity field. So that's how you couple the two things, and you solve these coupled dynamical equations numerically. And so by the way, that's what is model H. Okay. Now here is here are my results for three-dimensional diffusive coalescence mechanism in my vapor-liquid transition exhibited by the Lennard-Jones model that we have considered. And here I have plotted the average size of the droplets cube, or average volume of the droplets as a function of time that goes linearly. And we have argued in this slide in 3D, the exponent should be 1/3, and the volume is going linearly, that means length is growing as 1/3, okay. And a direct verification, so we have, more elongated trajectories. Basically here we have traced a trajectory for a single droplet over a period of time within which it didn't undergo any collision. So you can see there is some Brownian feature in the motion of the droplet. So essentially this directly verifies that it is a droplet diffusive coalescence mechanism, and it is giving rise to the expected 1/3 exponent as predicted by Binder and Stauffer. Now I come to the ballistic aggregation picture, which I argued, which I mentioned that will be valid when you have a quench to very, very low temperature. That may be possible when you have vapor solid kind of transition. Background density, vapor density will be very low. I bring in some relevance to the actual scenario. So this ballistic aggregation has its relevance in material science, in granular matter, in astrophysics, in so many different places. And there are two types of ballistic aggregation. One I prefer to call as ballistic deposition, which has relevance in material science. And so there basically from a certain height you drop particles, small particles, nanoparticles, and they get deposited on a substrate to form such kind of fractal pattern. And the kind of ballistic aggregation I am talking about, there the clusters themselves move. So here only one fractal cluster is forming, and that is growing with time. And so these are some pictures of asteroids. They are moving, and you can see they are not actually spherical in shape. They have certain degree of non-sphericity. That is analogous to saying that they have certain degree of mass fractality, okay. And here is the ice clusters that I have already shown to you, okay. And the kind of picture I am talking about, I am interested in, that is when these clusters as a whole they can move ballistically, and once in a while they will collide, they will stick to each other. In the astrophysical context, how can that happen basically? So when they collide, okay, there will be huge temperature rise in the boundary, and that heat will be, so there will be melting in the boundary region, and there is dissipation of heat to the environment. That way basically there will be solidification in that area, that way they will stick to each other. And on top of that, occasionally there can be fragmentation also, okay. So another more broader class of problem is this aggregation and fragmentation. So recently I have been interested in such kind of thing, but the kind of results I will present here, that is only the aggregation part, not fragmentation part, okay. And as I said, granular matter and astrophysics community are very much interested in such kind of ballistic aggregation. Typically in simulations what they do, they take sticky hard spheres, okay. And if you consider that, you naturally expect fractal structures. Hard spheres are moving, they are colliding and sticking to each other. That way basically you expect such kind of structures, and this is a result from simulation. But when you have, and when such kind of fractal structures do collide with each other, if it is a sidewise collision, you can easily imagine that that kind of collision will induce rotation in the system. And if you are dealing with hard sphere, you cannot perform actually time step driven molecular dynamic simulation. People do take the route of event driven molecular dynamic simulation, and in event driven molecular dynamic simulation, taking care of both the rotation of fractal clusters as well as translation, it becomes very difficult. So to avoid this difficulty, what people do consider, once two particles collide, form a dumbbell-like shape, they immediately by hand give a spherical structure to that, so that this difficulty of dealing with the rotation of fractal structures can be avoided. But when you do that, you actually lose the importance of fractality in the growth process, okay. Now, if you are able to obtain such kind of fractal structure in a natural way in time step driven molecular dynamic simulation, where your particles do interact via non-hard sphere like manner, then you can of course do time step driven molecular dynamic simulation, and you do not need to take care of the rotation of the cluster separately. Your evolution automatically takes care of such things, okay. And we encounter such kind of things. You can see these elongated clusters. These are basically some sort of mass fractals which are growing with time, and this occurs, growth occurs via ballistic aggregation mechanism. So these are results from snapshots from 3D, these are from 2D, and you can see if you zoom up small regions, you can see nice hexagonal periodicity. So then the question I asked at the beginning, and I promised to explain why such kind of fractal structure should exist. What happens? You have, let's start with a situation where you have liquid droplets in the vapor background. Two liquid droplets are colliding with each other. At the moment they collide, it looks like a dumbbell. By the time this dumbbell undergoes another collision, the constituent particles, since they are in a liquid phase, they are highly mobile. They can rearrange themselves to give this dumbbell a liquid shape by the time it undergoes another collision. But if your clusters are in the solid phase, okay, then the relaxation of related to reshaping the dumbbell is a very, very slow process. Okay, by the time, so the relaxation time within the cluster is a diverging quantity. By the time this dumbbell undergoes another collision, the shape remains more or less same. So in the next collision, it will get another side. That way basically branching will progress in all possible directions. and that gives rise to basically this fractality. On top of that, if the clusters do rotate, that gives rise to larger collision cross section, as opposed to if the same mass had been confined within a sphere. Okay? That way, number one, these clusters are moving very fast, and number two, because of the fractality, the collision cross section is getting enhanced. So that way, it's the growth is getting further enhanced. Okay. Now the picture is the following. How much time? 10 minutes?
We can discuss more.
Okay. I actually went very slow. Okay. In such a situation, it's better to look at the growth. You calculate the average mass rather than average characteristic length, the way typically it is done in phase ordering dynamics. There is non-scaling behavior of the correlation function, decay, so on and so forth, that may lead to misleading information. So anyway, you calculate the average mass or the average radius of gyration. Okay? So mass grows with time in a power law fashion with some exponent 1.15, and to obtain the fractal dimension, you plot the average mass as a function of the radius of gyration. On a double log scale, you see nice straight line, linear looking behavior. From there, the exponent is the value of your fractal dimensionality. And to confirm that the clusters are indeed moving ballistically, we look at the mean square displacement of individual clusters as a function of time. You can see over a long period of time there is quadratic behavior. That means they are moving unopposed. After a long time, there may be crossover to diffusive behavior, but you can probe significantly long time over which the behavior is like this, and then you can calculate the root mean square. Clusters themselves, there will be, slight change of fractality, that's what you mean, but
Look at the mean square displacement, not the one object. When you're looking at the mean square displacement,
yeah.
clusters are coalescing also at the same time.
Yeah, so this is over a period over which this cluster didn't coalesce with this.
That's why it's
Yeah. So as soon as they collide with other thing, we do not count this. Yeah. Then you can calculate the root mean square velocity of the clusters, plot it as a function of mass. Then it has this kind of behavior. This information will also be useful in the next slide. Then we go to the theory of ballistic aggregation. Like the theory of diffusive coalescence mechanism, it reads like this. You have average cluster density. It is decreasing with time because of the coalescence, dn dt, negative sign again because of the fact that the cluster density is decreasing with time, and simple kinetic theories.
This assumes, sorry, I shouldn't interrupt. This assumes a compact cluster, right? All of these theories assume a compact cluster.
Yeah, so this assumes compact cluster, okay? And with that, you cannot actually explain this 1.15 behavior, okay? So you have a collision cross section that has, if you do not consider fractality in the system, this collision cross section should go as mass raised to the power this, and then this VRMS for uncorrelated motion, it should scale with mass with some exponent -12. That's what we obtain here. And then cluster density should be inversely proportional to the average mass. If you plot all these things back here, you get an expression for beta like this, okay? And beta is the growth exponent for mass. And but if you put the value of dimension, we are working in 2 dimension here, the value of beta you obtain is 1, but here you get 1.15, and this number is very accurately estimated by a different kind of analysis, so it's not a numerical error, so there is some deviation. So this deviation can be explained by the introduction of fractality in the system. So if you introduce fractality, then the collision cross section slightly gets changed, okay? And as a result, your growth exponent turns out to be strongly dependent upon the system dimension as well as the fractal dimension, okay? And D is 2 here, of course. And then to verify this relation, you can actually do the simulation with different fractal dimension. How can you do that? See, I told you this fractality is occurring because of slow relaxation within the clusters. Now, if you vary the temperature, that relaxation time changes, and that can change the fractality of the clusters. Okay? So that way, you do the simulation at different temperatures, and from your simulation, you extract the value of beta, and at the same time, you estimate the value of fractal dimensionality. So, and put those value of fractal dimension in this expression and compare the two things, and they are in nice agreement with each other. Now I have asked the question.
I think we should start. This is a new topic, right?
No, I won't describe it actually. Yeah. Yeah.
Maybe we discuss after the...
Yeah. Yeah. So I have mentioned, so I have presented two different pictures. One is diffusive coalescence, one is ballistic aggregation. But I have mentioned that the motion of the clusters can be subdiffusive, super diffusive, super ballistic, anything. And there can be, a very continuous variation of the fractal dimensionality depending upon your temperature and many other factors. Now, how to capture those things? We have come across a situation where we have seen that in an active matter model, by varying the activity of the particles and the temperature and overall density, you can actually modulate the motion of the clusters quite nicely. That way you can capture the growth exponent in various different situations, but capturing the whole thing theoretically in a general situation is very, very difficult, but there should be effort towards that, okay? So that's what we are up to, and I would like to, so since the title of my talk says diversity in dynamics, as Bulbul mentioned that there exists reason behind the diversity in dynamics. I started with, kind of very nice universality in static critical phenomena, then pointed out that when you move to dynamic critical phenomena, dealing with equilibrium dynamics, the critical exponents are different for slightly different transitions. Then we move to far from equilibrium dynamics. I said that it's a whole zoo of things, very complex. Nevertheless, people do ask for universality. But even if the universality is very weak in dynamics, particularly in non-equilibrium dynamics, there should be effort to find out at least the scaling laws that as they exist in static critical phenomena. And in static, there exists very well set of scaling laws. In dynamics also such things do exist, but it's far from being complete. One reason, of course, is that the diversity is too much. And this is, for example, one kind of hyperscaling relation with respect to the exponent, but it's a very weak one in the sense that if we go here, so this is the value of expression for the exponent we obtained, but it need not be always a power law. We solved an equation in a simplified form where we wrote down an equation, arrived at an equation dm dt is something like this. But depending upon the value of df, the equation can be of the type dm by m is proportional to dt. Then what will be the solution? It will be an exponential solution. People do refer to that as explosive growth. Okay. Nevertheless, better relation involving, so this growth exponent is not the only exponent for this far from equilibrium dynamics. There are exponents related to aging, persistence, pattern, so on and so forth. I mean, this is a very, I mean, everybody can write down by slightly modifying the Smoluchowski equation, but more robust scaling relations like this in the non-equilibrium context can be obtained, and there should be effort towards that like it was there in critical phenomena. So that's what I want to mention, and with that I summarize by just putting down the slide here. Yeah? Yeah, so simulation is you have this growth data. From there, either by putting on log or by doing different sort of analysis, you extract the value of beta. That is the red, those are the red symbols. And then from the same simulation, you calculate the fractal dimension and put those numbers here. Okay, then plot them. Okay, those are the blue symbols.
You measure the fractal dimension at different temperatures.
Right. Yeah, it changes continuously with temperature, but if you go to reasonably high temperature, you cannot actually get the ballistic regime for extended period. You enter the diffusive coalescence mechanism. So one needs to be careful about what regime you are, and yeah.
The DLA.
DLA is, yeah, so the particles basically, so in DLA what happens, DLA has different versions basically. The most original version is that you have a fixed seed and individual particles are moving diffusively. So it's more like a counterpart of this. Then you will fall in the diffusive coalescence mechanism. So you will encounter vapor-liquid transition. And the clusters will be spherical, they will move diffusively, so on and so forth.
So there was, saw that like when you went to the lower temperature, the deviation of the motor in the theory. Is that a trend or is it?
It can be, I won't like to comment on that, it can be numerical error or, I don't know, but here it looks like the deviation is systematic. And the other thing is also that depending upon the temperature, so this quantity, this VRMS, that has also deviation from this minus half exponential. Yeah. So it requires, I mean, a lot more careful analysis actually. So this is reasonably true at one particular temperature, and as you can see, compared to other data, other results, this data are rather scattered, and it's little hard to say how close they are to one half. So it's about diversity of dynamics. One particular thing I wanted to mention, which I said at the beginning that I will be able to talk about. So that is related to the roughening transition. If you have conserved order parameter dynamics, ordering of Ising ferromagnet, you expect T raised to the power half behavior. Now recently we have encountered that when in 3D there is a non-zero roughening transition. This particular problem drew attention of various people. They tried to get various different features. For example, 3D Ising model, if you coins to zero temperature, the systems never reach ground state if you do spin flip dynamics. And people.
The roughening transition at zero temperature.
No, I'm coming to that. And then people did report that for 0 temperature in D equal to 3 non-conserved rising model, the growth exponent is 1/3. So we got interested in looking into those sort of anomalies people did report. So there actually we understand the phenomena this way, that actually in the asymptotic limit in the growth exponent is 1/2 we have established. But what is happening, the aging exponent changes. That is because below and above the roughening transition, the interface structure is different, and there is something called Ota-Jasno-Kawasaki function that describes the non-equilibrium correlation function. It doesn't match with the result when you are simulating the system below the roughening transition temperature, and this aging exponent is highly dependent upon the correlation function. Okay, so that's another, recent work where, we tried to show how structure can bring in huge diversity in the dynamics of growth. Yeah.
Clusters there are compact or?
Clusters, this activity actually enhances compactness. But then again, you can modulate that by lowering the temperature and modulating the activity parameter. It depends upon model. So I'm talking about the Vicsek activity. Okay, so there, so this model is this Vicsek activity is combined with Lennard-Jones model. Okay, there is passive interaction also. So by combining or playing around the strength of the Lennard-Jones and the Vicsek activity parameter and overall density and temperature, you can actually modulate the fractality and the motion of the mean square displacement behavior of the clusters.
So these fractal structures are also possibly higher where, for example, in gelation. So you have this quenches from high temperatures, and there basically the liquid is sort of fracturing. And this, for example, Karmakar calls this viscous fracture. There also you can get this.
Yeah, but there the mechanism as a whole is different. So there will be interconnected structure. So that way basically it will play a role, far less important role in the sense that fractality you can attribute, you can call it like surface fractality in interconnected structure. But here you have completely disconnected structure, and this fractality is basically enhancing the collision cross section. But there is no collision picture. Yeah.